This is Naresh, working as assistant professor in IAC department. And today's topic is Zener diode characteristics and how it is acts as a voltage regulator. So, in the last classes, we observed that some of the semiconductor devices like a PN junction diode, and it is also called PN diode, or it is also called normal semiconductor diode. And we observed that some bipolar junction transistor as well as a field effect transistor. And similar to this in a PN diode, when we consider the normal PN junction diode, we use two different types of the materials. One is P-type material, another one is we use that N-type material. And we are intersecting these two materials, means whenever we are interconnecting these two materials like P-type material and N-type material, it becomes one junction. The junction is called as a PN junction, and it is also called as a PN junction diode. And due to this intersecting of two different materials and the doping concentration, and we observe that the characteristics of the normal PN junction diode. For this normal PN junction diode, this PN junction diode is conducts only in a one direction, that is known as a forward direction. In a reverse bias, there is no flow of current across the PN junction diode. Hence, the PN junction diode works under only the forward bias, and there is no flow of current across the reverse bias. And here the Zener diode is specially designed to allow the conduction in both the directions, that is under the forward bias as well as the reverse bias. And to design this Zener diode, it also uses the P-type material as well as N-type material. But the difference is the doping levels are different in a normal PN junction diode as well as the Zener diode. So that is the reason the breakdown, or how much that breakdown voltage, here it is also called as a Zener voltage. And here we are saying that how much voltage is required, means what is the breakdown voltage. If you consider in a normal PN junction diode, the cut-in voltage is represented as either 0.7 volts or a 0.3 volts, 0.7 for silicon type and 0.3 for zirconium. And in this case, we are observing that, and that breakdown or a Zener voltage is identified depends upon the doping levels. And we know that what is the doping, means adding the impurities to the pure semiconductor is called as doping. When a trivalent impurity is added to the pure semiconductor, then we define as that is a P-type extrinsic semiconductor. When a pentavalent impurities are added to the pure semiconductor, is called as a N-type semiconductor. So like that. So in this case also, we are increasing the doping levels to satisfy the characteristics of Zener diode under the forward bias as well as the reverse bias. Then, in this case, let us consider some of the important points. When, if the diode is heavily doped, then the depletion layer should be very thin. So, means the depletion region, it becomes very thin. As well as consequently, the breakdown of the junction will occur at lower reverse voltage. Means, so the doping levels are heavily doped, means the depletion region, let's take this is the depletion region. The depletion region becomes very, very small, hence it requires a very less reverse voltage to allow the conduction across the reverse bias. So that is the reason we are applying the reverse voltage to allow the reverse conduction. Then, and one more point to observe in this case, a lightly doped diode has a higher breakdown voltage. Why? Because of that, if the doping concentration is more, the depletion layer becomes very thin, hence it requires a very small reverse voltage to break down the condition. And similarly, if the doping materials are very small, means that is the reason it is called as a lightly doped material. Hence, it equals whenever the doping levels are very small, that depletion layer becomes region becomes very depletion layer becomes very large. Hence, it requires a higher breakdown voltage to diffuse the charge carriers from the one region to the another region. So that is the reason. So for this case, to satisfy this Zener condition or to allow the reverse bias characteristics, a normal diode is properly doped. Then it is called as a sharp breakdown voltage, and based on that particular diode, here it is called as the Zener diode. Then from that all these points, here I representing that a Zener diode is a type of diode that permits current not only in the forward direction like a normal diode. Means that if you observe the normal PN junction diode, we know that when the diode is a forward bias, then it allows the conduction, means conduction rate is increases when diode is under forward bias. Similarly, when the diode is under the reverse bias, there is no flow of current. Hence, based on that condition, diode allows a conduction in a forward bias. Then, under the reverse bias, it acts as a open circuit. So that is the reason a Zener diode is a type of diode. It permits not only in the forward direction, means so it is specially designed for to allow the conduction in both the directions. That is forward direction as well as the reverse direction. So that is the reason, but also in the reverse direction. In this case, we take an as when this diode becomes conducting, and for this case to allow the conduction, so we need to apply. And so let us case if you consider the normal PN junction diode, and we are let us say this is the normal PN junction diode, P type material and N type material. To identify the characteristics, we applied some amount of biasing under the forward direction or a reverse direction. Let us consider here I'm applying the forward bias direction, and we know that if you want your up means if you want to make the diode in the conduction, your input voltage must be greater than of cutting voltage, that is either 0.7 volts or a 0.3 volts. Then only the diode becomes or the diode is enters into the conduction state. The state is represented as on state. So similar to that, in this case also, for to identify the Zener condition, so to allow the characteristic or to allow the conduction under the reverse direction, then we designed for this Zener diode. So for this case, your applied voltage must be larger than the given breakdown voltage or is Zener knee voltage, or that voltage here it is also called as a Zener voltage. That is the reason after this characteristics and based on this current voltage or a Zener knee voltage, this device is named as a Zener diode. Now this is the symbolic diode of the Zener. So means it contains like this, and in the cathode side it looks like some Z model, and here this is P type material and N type. It is represented as anode and it is represented as cathode. The breakdown voltage here it is represented as Zener voltage or VZ. Now we'll see the characteristics. So means now I'm going to utilize the Zener diode. Means here the Zener diode is acts as a forward bias, as well as the Zener diode is also under the reverse bias. Means to identify the characteristics or to identify the behavior of any semiconductor device, we need to apply some amount of the biasing voltage. So means what is the meaning of biasing? Means the way of approaching some external force to a semiconductor device is nothing but your bias. And in the case based on the principles of normal PN junction diode, and we have the two materials, P type material and N type material. When a P is biased with the positive pole of the battery, then N is biased with the negative pole of the battery, then we can say that this is a forward bias approach. Similarly, when a P-type material is connected to negative pole of the battery and the N-type material is connected to positive pole of the battery, then we can say that that type of the biasing is called as a reverse bias. And by using this principle, now we are going to observe the Zener diode characteristics. So let us consider. Here I am going to consider this Zener diode, and it is represented as the anode, and this is the cathode. Now I am going to apply a biasing voltage between anode and the cathode. Hence, the anode is made with respect to the positive pole of the battery, and a negative pole of the battery is connected to cathode side, and we are applying a DC voltage source. It is represented as a Vin, and then I am going to measure a output voltage across this load resistance, and from this point we can say that the Zener diode is acts as a forward bias. Under this condition, and here this Zener diode means, if you understand this principle, let us consider in the normal PN junction diode. We know that in the normal PN junction diode, from normal PN junction diode, under the forward bias, so when your applied input voltage is must be greater than or equal to cut-in voltage of your given PN diode, then only the diode becomes forward bias. Hence, the state is represented as on state. If it is on state, it allows the maximum current. That current is represented as maximum current. Similarly, when your applied input voltage is less than of your cut-in voltage, then the diode becomes a reverse bias. If the diode is a reverse bias, means there is no flow of charge or a current across the PN junction diode. Hence, the state is represented as off state. Hence, the current is represented as 0. That reverse current is represented as 0. And based on this PN junction diode characteristics, if you want to draw the characteristics, and x-axis is represented as the forward voltage across the diode, and the y-axis is represented as the forward current across the diode. And we know that, so, and at this point, we know that, so let us take this is the current voltage of a PN junction diode. Either it is 0.7 volts or a 0.3 volts. This is for silicon and this is for germanium. At this point, when your applied input voltage is equal to or greater than of this current voltage, then only the conduction rate is increases, hence the exponentially the current is increases under this forward bias. And up to this, if there is less than of your current voltage and there is no current, hence the current is represented as 0. This is the reverse current is represented as 0. So similar to that, when a Zener diode is biased under the forward bias, it also looks like a normal PN junction diode. Hence, the characteristics of this Zener diode looks like a normal PN junction diode under the forward bias. So hence, if we let us consider the same characteristics of this Zener diode, let us consider. So I'm going to consider the x-axis is represented as a VF, the forward voltage across the Zener diode, And the y-axis I represented as the forward current across the Zener diode. Hence, the Zener diode forward bias characteristics are looks like your normal PN junction diode. Hence, after the cut-in voltage, then a exponent means a conduction rate is increases. Hence, this is represented as forward current. And similarly, if when the Zener diode is connected under the reverse bias, let us consider that if I take and this is a normal, so this is Zener diode, and we know that this is anode and the cathode. Then I'm going to make the Zener diode is under reverse bias, means anode is connected to negative pole of the battery with respect to the cathode. So hence the positive pole of the battery is connected to cathode terminal as and a minus. Then we are going to measure the output voltage, the Zener voltage across the load resistance under this biasing condition. So at this point, the way of approaching of this external DC source to an Zener diode, under this condition, here the Zener diode is acts as a reverse bias. So means here the Zener diode is entered into the reverse bias, and here this Zener diode is especially designed for to allow the a conduction in forward bias as well as reverse bias. If you observe the normal PN junction diode, and due to that the way of approaching the biasing to a normal PN junction diode. So under the reverse bias condition in a normal PN junction diode, the depletion width is increases. So hence there is no movement of the charge carriers from the one region to the another region. All the charge carriers are diffusing towards the battery side. That is the reason there is no flow of conduction takes place across the normal PN junction diode under the reverse bias. To overcome this drawback, so here this Zener diode is designed with a heavily doped compared with a normal PN junction diode. That is the reason if the doping levels are changes, then what happens if the diode is heavily doped, then it forms the very thin depletion region. So that is the reason. Due to that, the formation of very thin depletion region due to this doping concentrations, and it requires a very small reverse voltage to break down the diode properties, means the region. Hence, whenever the diode is a breakdown, then it allows the maximum current is flowing through this condition. Hence, let us say in a normal PN junction diode, the breakdown mechanism is called as a avalanche breakdown. But here, for this Zener condition, the breakdown is represented as a Zener breakdown. So at this point, whenever it enters into the breakdown region, means your applied voltage is equal to your voltage across the Zener voltage or the breakdown voltage. Then the Zener diode now starts the conducting, means now the diode is replaced with the on state. Means whenever your applied input voltage is approximately equal to Vz, then the Zener diode acts as a short circuit. So it acts as a short circuit, meaning that state is represented as on state. And whenever this VA is less than of this Vz, the voltage across the Zener, that is reverse voltage. Now the Zener diode acts as an open circuit, the state is represented as off state. Hence, whenever it is conducting, the maximum current, means the conduction rate is increases very sharply So this type of representation means, so hence if you observe these characteristics of this Zener diode, it allows the maximum conduction in either forward bias as well as the reverse bias. So, so here I shown in the detailed characteristics. So this is I consider it looks like normal PN junction diode characteristics. Hence that is the reason I consider the cutting voltage is in between the 0.3 to 0.7, and under the reverse bias, and we know that the breakdown region or the breakdown voltage, that breakdown region or a breakdown voltage is represented as a Zener breakdown voltage. Whenever your applied input voltage is crosses this breakdown voltage, then the conduction rate is linearly increases. At this point, it maintains a constant output voltage. So this is Zener diode characteristics under the forward bias as well as the reverse bias. So from this we observe the sum of the point. So what are the parameters we observed up to this point means under the forward bias condition as well as under the reverse bias condition. Based on that, so we identify that when the reverse bias on a crystal diode is increased, and that is nothing but your breakdown voltage, it means whatever the voltage means, the reverse voltage. So let us consider this is the Zener diode, and for this case we are applying the reverse voltage, means we are increasing this reverse voltage, and that increased reverse voltage is reached to your breakdown voltage or a critical voltage. Then what happens here, the reverse current is increases sharply whenever your applied input voltage is just reached to the current voltage or the breakdown voltage of the Zener diode. Then the reverse current is increases to maximum value. So that we observe from the characteristics. So hence like this. So this is I consider the VZ, and this is your applied input voltage under the reverse direction. When this applied voltage is crosses this Zener voltage, then a sharp linear increment of current, that is a reverse direction. So hence that current is represented as a reverse current here. And one more point, the breakdown region is of the knee is we are going to show here, and the breakdown voltage, so that is also sometimes we can also call it as a Zener voltage, and a sudden increase in the current, so means this is a sudden increment. So up to this point, when your applied voltage is reached to Vz, there is no flow of current or there is no flow of conduction across the Zener diode. But whenever your applied input voltage is reached to the cutting voltage, a sudden increment of current is changes. Hence, that current here it is also called as Zener current. And at which point the conduction rate is sharply increases, and that point, that particular voltage, here it is called as a Zener voltage. So that is the reason. This point we represented that a knee point, and at this knee point, after this knee point, the Zener current is sharply increases. So hence, at which point a sharp linear current is flows, and that particular voltage here it is represented as Zener voltage. So up to this point, we observed the, so what is the difference between normal PN junction diode and Zener diode here. Then we also observed the characteristics of the Zener diode. Then based on all these points, we observe some of the points. So the first point is, and the Zener diode is also like acts as a ordinary diode except the properly doped. So means we need to differentiate between a normal PN junction diode and a Zener diode. If you observe these two diodes, in both the cases we have the same materials. P-type material as well as the N-type material. But we need to show some differentiation in the way of conduction. So to change the conducting or to change the property of the diode, so here we modified as the doping levels. So that is the reason to satisfy the properties of the Zener diode. So we need to make sure that the doping levels we need to concentrate. So we need to differentiate the doping levels between the normal PN junction diode and a Zener diode. So in a Zener diode, we consider that the doping levels are very high compared with the normal PN junction diode. And one more point we need to conduct, the Zener diode is always reverse connected, means we need to show in a reverse bias direction. Then at this point, we observe that it contains a sharp breakdown voltage, and that point here it is also called as a Zener voltage, that is represented as Vz. Now, again, one more point we observed from that a Zener diode characteristics. When the Zener diode is a forward bias means, so let us consider, and this P type is connected to positive pole of the battery, and this N type material or cathode is connected to negative pole of the battery. Then we can say that this is under the forward bias. Under this forward bias, and from the characteristics, what are the characteristics we observed? So this is the cutting voltage either 0.3 or 0.7. So it looks like a normal PN junction diode characteristic. That is the reason. When the Zener diode is forward bias, the characteristics are just those of ordinary, means it looks like a normal ordinary PN junction diode. So then we need to replace, means when if you want to identify some applications of Zener diode, then we need to replace in a similar case. If you want to identify the application of the rectifiers like a switch, the simple application, the PN diode is acts as a switch, means how we are going to replace this one. Let us take this is normal PN diode. So means it should be replaced with either switch, means either we need to make short circuit or we need to make open circuit. Means the way of approaching the external force to an PN junction. So when P is connected to positive pole of the battery, N is connected to negative pole of the battery, this diode is replaced with the equivalent circuit, is replaced with the short circuit. At this point, the state is represented as your on state, along with it contains a current voltage. Under the diode is forward bias. Similarly, when a PN junction diode is reverse bias, means a P is connected to negative pole of the battery and N is connected to positive pole of the battery, then we can say that this diode is acts as a reverse bias. Under this bias, we know that the diode is replaced with the open circuit, hence the current flowing across this device is zero. So similar to that, we need to identify the two states, on state. So how we are going to find out this on state means when the reverse voltage across the Zener diode is equal to or more the breakdown voltage, then so from these characteristics, what we observed from the characteristics, so let us consider at this point, and we observe under the risk reverse direction, your applied input voltage is reached to the current voltage or is more than of this current voltage, or whenever it produces a sharp or linear increment of the current, at that point we can say that Zener diode is replaced with short circuit. That state is also called as your on state. So that is the reason when the Zener reverse voltage across the Zener diode is equal to or more than breakdown voltage, that is Vz, the current is increases very sharply. So that is the reason at this point we are going to replace that diode is replaced with the voltage source that is equal to Vz. So therefore, in the normal breakdown region or in ideal Zener diode, so we are replacing with a battery, means it acts as a voltage source. So that state is represented as here the on state. Now Coming to your applications, means where we are going to use this Zener diode. Suppose if you observe a normal PN junction diode, a normal PN junction diode can be used as either normal a switch or a rectifier line. So here the Zener diode can be used as a voltage regulator. So means in the case of power supplies, a regulator power supplies, we need to use this Zener diode. So what is the meaning of voltage regulator? Means it regulates the voltage, means it maintains a constant DC output voltage irrespective of the variations in the main power supply or the load. Then we need to maintain a constant DC source. So that can be observed by using the xenon diode. Then to satisfy this voltage regulator, so we need to connect the Zener diode is under the reverse bias. That is the reason the Zener diode of voltage is reverse connected across the load resistance to maintain a constant output voltage. So that is the reason to satisfy the voltage regulator, the Zener diode can be under the reverse bias condition only. Then at this point, the series resistance is absorbs the output voltage fluctuations, so to maintain a constant voltage across the load. Let us consider we have the two circuits to satisfy the a voltage regulator. So we have the two resistances here. One is input resistance R, and another is the load resistance, or it is also called as output resistance. And in this first diagram, I connected the Zener diode is under the reverse bias direction, means that the anode of Zener diode is connected to negative pole of the battery. Similarly, the cathode of Zener diode is connected to positive pole of the battery. When this applied voltage, here I consider the EI is must be greater than or equal to the voltage across the Zener diode or a Zener breakdown voltage. Then we know that the Zener diode is replaced with the on state, or it is also acts as a battery source when that is fully charged. Then that is represented as your VZ. So hence under this condition I replace with. So whenever your applied voltage is reached to the Zener breakdown voltage or a current voltage, this Zener diode is replaced with a equivalent circuit, that is a voltage drop. Means at this point the voltage becomes constant. So whenever the Zener diode enters into the Zener breakdown region, the voltage becomes constant. That voltage here it is represented as VZ. So that is the reason. So from that given input voltage, we are increases. Then the Zener diode in the breakdown region. Hence, we represent it as the Zener diode is equivalent to battery. What we shown here, the same parameter as represented. Then, so from this observation, from this graph, from this equivalent representation, so to identify this output voltage means whatever the output voltage E naught or a V naught, that is approximately equal to the voltage across the Zener diode. So means the voltage across the Zener diode is VZ. Means whenever the current is a linear, sharp current is increases, at which point or at that point the voltage is acts as a constant output voltage, that we consider as the output voltage. Hence E naught or a V naught is equal to Zener breakdown voltage. Then so this will cause the increase in the value of total current I. Then the Zener will conduct to the increase of current I while the load current remains constant. So that is the reason the output voltage that remains constant irrespective of change in input voltage. So here we maintain as the load resistance the constant, and whenever the Zener diode is enters into the breakdown region, irrespective of the change in. So up to that VA is reached to VZ, the Zener diode is acts as an open circuit. So when until your applied input voltage is reached to the cut-in voltage or Zener voltage, then the Zener diode is acts as the off state, hence there is no constant output voltage in the product. That output voltage, so when the diode is a reverse bias or open circuit, that output voltage across the diode is approximately equal to your applied input voltage V. But when your applied input voltage is reached to Zener breakdown voltage or more, then the output voltage is approximately equal to the breakdown voltage of Zener diode, that is equal to Vz. Means, and at this point, when the Zener diode is reached the cut-in voltage, then it becomes the voltage drop across the voltage side becomes constant, irrespective of the change in power supply variations. Now, from this circuit, if I consider, then we need to calculate the voltage drop across R from this representation when your Zener diode enters into the cut-in voltage. At this point, we need to calculate the voltage drop across this resistance. V is represented as, so what is this one? The potential difference between. So means what we represent here, this E naught is equal to Vz. Means we have the two voltage sources here. One is EI, another one is E naught. So hence the potential difference between these two voltage sources is nothing but the voltage drop across R. Hence the voltage drop across R is represented as the potential difference between your applied input voltage and the output voltage across the load resistance. Similarly, if you want to calculate the current flowing across this device, so hence the current flowing through R. So I means, so what I meant this one. So at this point, I is so this direction, and these are the at this node these are the two entering points. What are the entering points? One is IZ is entering, one is IL is entering, and the leaving current is high. So according to KCL rule, the leaving current is equal to entering current, hence, and this current entering through the resistance, that is represented as I is equal to, so the leaving current, so entering currents are, the leaving current is I and entering currents are IL. That means the current across the load resistance as well as the current across the Zener diode, that is represented as IZ and IL. So the current across the Zener diode is represented as IZ. The current across the load resistance is represented as IL. So that is the reason the current flowing through the input resistance is represented as I is equal to IZ plus IL. So based on that, if you apply the Ohm's law, then I'm going to calculate R. So R means there is nothing but we know that R is equal to V by I. So V naught, V means we identified that the voltage drop across this resistance is represented as EI minus E naught, and the current flowing across this resistance is represented as the summation of Zener current and the load current. Hence, I substituted according to Ohm's law, R is equal to V by I. In the place of V, I substituted the potential difference between input voltage and output voltage. In the place of I substituted the current flowing across Zener and load. So at this point, we use that your input voltage and the load resistance is a fixed. Then, so based on this condition, we find out that, so at which point the Zener diode is accessed on state. Then from there we calculated that the output voltage across the Zener diode. So hence, for this case, let us consider. So when we means that in this condition, so this is the Zener diode. So negative is connected to anode and this is the cathode. And at this point, so up to this, when EA is less than of VZ, the Zener diode is acts as the open circuit. When EA is reached to VZ or more than of this VZ, the Zener diode is acts as a short circuit. So that from that, so here I am representing that the V naught is equal to, so or E naught is equal to, means the current flowing here, means how to write this V naught or V naught is equal to I into RL. So the current flowing through this load resistor. So what is I? So I means V by R. V means the potential. So input voltage is EI by R means the total resistance R plus RL. Hence the V naught or E naught is equal to RL into EI by R plus RL. So at this point, what happens? So RL becomes a constant and EA is a constant. Then that is the reason V is also becomes constant. Means it stabilizes the DC output voltage. From that, we can say that the Zener diode is acts as a voltage regulator. So up to this point, today we discussed that what is a Zener diode and how to build the means how to design the Zener diode. What are the doping levels are required to design a Zener diode, and we also observed the characteristics of the Zener diode. And based on the characteristics, we observed that the application of the Zener diode is acts as a voltage regulator. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.